So the idea is if I'm standing on a scale in an elevator, I feel gravity pulling me down. Right? And then if everything's fine, the elevator is just sitting there. I mean, not that it wouldn't be fine if the elevator was moving. I'll feel a normal force from the surface. Yeah. Now, if this elevator were to be accelerating upwards, let's say, physically speaking, I mean, intuitively, it not only has to, so you see when I'm standing on the elevator, the ground has to balance how hard gravity is pulling at my legs, right? If there was no ground, or if the floor of the elevator gave way, I would just fall right through. So Fs has to be at least mg if I am to be standing where I am without the floor of the elevator just falling away. And if Fs is more than mg, I'm just and the elevator is not moving, that means suddenly I'm flying off, I'm Superman. Clearly that can't happen either. So Fs has to be equal to mg exactly. However, if the elevator starts accelerating upwards, not only does the floor have to balance gravity's pull on me, it also has to push me up a little bit more to give me the same acceleration A that the elevator has. Yes? So if I write down the equations of motion, and again, if you look at the free body diagram, I have an Fs pointing upwards, mg pointing downwards, and assume I take the upward direction to be positive. Consider this to be the positive y direction. And I sum up all the forces, I have a plus Fs minus an mg. And if I'm accelerating upwards, this has to be equal to plus m times a. Right? So all in all, the amount of force that the floor of the elevator exerts on me is equal to not just mg, but there is an additional ma that comes into the picture. So I actually end up feeling heavier than I really am. And you can, of course, quickly work out the equations for when the elevator is accelerating downwards, or if it's slowing down. Then you would see that and this is something you can try out. You can step into an elevator, preferably that goes to the top of a high building, and you'll actually feel heavier when the elevator starts accelerating as soon as the doors shut. Now there's a few other situations where this sort of a situation, this sort of a phenomena can happen. For instance, imagine you're sitting on a Ferris wheel. Let's see. So imagine you're sitting on a Ferris wheel. You're on a vacation. If you were at the bottom, you're at the bottom, right? Let's draw a free body diagram and assume this Ferris wheel is going around with, So at the bottom, let me draw a free body diagram. If I'm sitting on a chair, the chair is holding me up, right? So I don't fall to the ground. Gravity is everywhere, so gravity pulls me down. And there's a normal force on me from the chair, so that the chair, holds me in place. What else? Am I missing something from this picture? Is this all there is to it? The Ferris wheel is spinning with a constant speed v. What else must I have here? Speak up, I can't hear you. This thing's making a lot of noise. I really can't hear you. You have to speak up. So there's a velocity, there's a speed, and there's a velocity. So what happens because of that? It's going around. There's a centripetal acceleration, yes? You had a question? Yes. So there is, yeah. So we seem to agree on that. There's a centripetal acceleration that must be making me and the Ferris wheel going around to go around in a circle. What direction would this acceleration be in? Towards the center of the Ferris wheel, right? So if I'm at the bottom, the acceleration would point vertically upward. And again, I'm assuming that any vector pointing vertically upwards is positive. So let me write down Newton's laws for this. Plus Fs and minus mg. Plus Fs because the normal force pushes me up. Minus mg because gravity tries to pull me down. This must be equal to MAC. Now AC has the value v squared over r, where r is the radius of this Ferris wheel, or approximately how far away I am from the center of the Ferris wheel. But we are not concerned with that, with the specifics of that. We really want to see how the notion of weight depends on where I am in the Ferris wheel. And given our notion of weight, which is tied in very strongly to how we feel, then that's really the normal force that the ground exerts on us. That really gives us the perception of weight. We see that it's mg, not just mg, but a little bit more that's coming around because of the centripetal acceleration. So we actually end up feeling heavier at the bottom. Now, the last time I was on a Ferris wheel was a long time ago, so I can't tell you experimentally if, from recent memory, but if you have been on a Ferris wheel recently, you probably have felt this. Instead of a Ferris wheel, you could also think of a swing, clearly much more easily accessible. So go to a park, kick a child off a swing and go sit on it yourself, and then sort of swing around, and you will feel that you actually are heavier at the bottom than you are towards the ends of your trajectory. What happens at the top? Okay, how should gravity act on me? Always downwards. I'm still sitting on my chair, so how would the normal force act on me? Upwards. And if I'm at the top and I'm spinning, how would centripetal acceleration act? Down towards the center of the wheel, right? So this is AC. Now if I write Newton's laws for this particular situation, again assuming that all the vectors pointing upwards are positive, I would have Fs minus mg, and this must be equal to, does AC point upwards or downwards? Remember, acceleration is a vector, so it should be minus mac. So do I feel heavier or lighter? Do I feel heavier or lighter when I'm at the top? should feel lighter, right? So here I feel heavier, and here I feel light. So somehow I seem to lose weight. Of course, an extreme example of this would be if I'm standing here, I have a normal force from the surface, from the ground pushing me up. I have gravity pulling me down. My weight I feel is mg. What happens if I were to jump out of a building? How much weight would I feel? Huh? This can be a good experiment if someone's willing to try this out. What happens if I jump out of a building? Anyone jumps out of a building. How heavy do you think? I would be weightless. For the few short seconds before I fall to the ground and something very bad happens, I would be perfectly weightless. Don't do this. I mean, just because I said it's a good experiment, don't go try this at home. But yes, that is in fact true. What you could do is if you have a spring balance or something at home, you can build an apparatus, hang something off of it, and drop it. And you would see that as the object falls, the balance reads exactly 0. There is 0 weight on that the object feels. When I was in high school, when I was in class 9, I think one of the groups from our class 10 batch, they had put together an experiment. It's actually damn nice if you try it out. It's really simple. It's very illustrative. Another kind of situation that one could encounter is, let's say, I'm driving. I'm driving with a constant speed v, right? And then the road sort of takes this weird dip. And if I consider the situation at the bottom of the road, am I on a straight path or am I on a curved path? I'm on a curved path. So if I'm traveling at constant speed on a curved path, what is the first thing that should come to your mind? Centripetal acceleration, right? So I'm going at constant speed towards the right. Gravity pulls me down. The normal force from the road holds me up. If there is no normal force, I'd probably sink right through. And I feel a centripetal acceleration, right? So what direction? Upwards. Why is that? Right, it's an arc, right? So this is part of a circle. It points to wherever the center of that circle is. So if I'm right at the bottom, AC points vertically upwards. Okay. So you have the free body diagram now. So take a couple of minutes, see what equations you get, and see if I should feel heavier or lighter at the bottom of this row. All you have to do is figure out what direction is positive or negative for you, and then write down your vectors accordingly. So just write down sum of all forces must be equal to mass times acceleration. What do you predict? Do I feel heavier or do I feel lighter? Anyone? Yes. Heavier. So we have one prediction, and he says I should feel heavier. Anyone who disagrees? Okay, let's work it out. So if I consider upwards to be positive, then I can write down the sum of forces is Fs minus mg. Right. This must be equal to mass times acceleration. In this case, the acceleration is centripetal acceleration. Again, pointing upwards, so it's positive. That means my weight, which is given by Fs, is mg plus mac. So I feel heavier. You can consider a similar situation, except now you're going, you're climbing a hill and you're at the top. So right at the top, I would have mg pulling me down. I would have the normal force from the ground pushing me up. And how would the centripetal acceleration look now? Downwards, towards the center of the circle that this arc is part of. So if I write the equations of motion, it would be Fs minus mg must be equal to minus mac. Minus because the acceleration vector points downwards. So Fs is now mg minus mac, which is a bit less than mg. It could be a lot less than mg depending on how high you, how fast you go. Remember, AC is v squared over r. So if I'm going too fast, what danger do I face? What kind of danger can I possibly be in? Yes. I could just go flying off the hill, right? If I'm going too fast. Why is that happening? Because if v is too large, it is possible that mac becomes at least as large as mg, right? And at that point I feel weightless. There is no normal force. I just go flying off the hill. I've lost contact. So this can be a far more dangerous situation. But assuming we are not going terribly fast, I would feel a little bit lighter at the top. So far, so good. Any questions? I think we're mostly doing stuff that you've seen before to some extent. We'll do a few more, probably a bit more involved examples than this. But before we get there, okay, so have you done the pulley problem? You have a pulley, you have two masses hanging off on one on either side. You have not seen that? Yeah? Okay. This is a little bit of a tangent, but imagine I have a pulley. And I take a very light rope. I tie each end to two different blocks, and then I put the arrangement on top of this pulley. Assume there is no friction at the pin. The pulley is free to roll. Very intuitively, if I take two blocks of exactly the same mass, and I just place it on top of the pulley, what would happen? The blocks have equal mass. I tie them to a string, and I place the string on top of a pulley. What do you think would happen? They would balance each other out. In a sense, you would really not see anything very interesting, yes? So by balance, what I think we all can understand is that there is no net force that each of these objects experiences. So let's see if we can work it out. So let me consider first the more general situation of M1 and M2, and M1 and M2 are not equal to each other. And then we'll see how the balancing situation comes about very naturally if we consider something like this. Let's draw free body diagrams. So let's draw a free body diagram for M1. M1 would feel gravity pulling down. And there's a tension TL. So if you try to take a string and then pull, right, at the point that it becomes really taut, you will feel it resisting, right? Why aren't you able to pull it even more? Because there's tension in the string that's pulling your hands back in. Beyond a point, you really can't make it tauter than it is, right? So that is really the idea of tension. It's the nature of a string to resist any changes in its shape when you apply a force. So assume this side of the string has tension TL, okay, TL, L for left. And the other side of the string has a tension TR. And I'm going to say that the string is so light that I can assume it's massless. No string is exactly massless, of course, they all have some mass. But the approximation works surprisingly well given the regular sizes and weights of day-to-day objects that we use. So I'm going to assume that the string is massless. And that gives me something very important. I'll show you in a minute what I mean. So what happens if I assume it's massless? Is there any reason for me to imagine that the tension on this part of the string and this part of the string, is there any reason for me to assume that they will be the same at all? Who says yes? Well, who says no? One half no. Okay, in general, there is no reason for me to assume that they are the same. But if the string is massless, we can in fact show that assumption is valid. So this assumption has the massless string assumption is very useful. Okay, so to show this, let me take a simpler example. I take a block, I attach a string to it, okay, and imagine that the string has different tensions at each point. Okay, so there's some tension right at the point where it's attached, there's some tension a little bit above that point, there's different tension all the way up here. Let's say at some distance away from where the block is, I consider the tension to be T. And the force of gravity on the block is mg. So if T is not the same as mg, because exactly at this point, and assume this is an equilibrium, right at this point, T must be the same as mg, exactly where the string is tight, right? Because that's where the string exerts a force on the block. So I'm saying if this tension is different from the tension of the string right at the point where it's tied to the block, then T and mg can't be the same. So there is a imbalance in the force. That's delta F. So this is somehow being used up by the string. And I mean used up in a very loose sense. Force is not like energy or something that it can just be used up. Used up, I mean that there is part of this force that that should be equal to mg but goes into doing something else on the string itself. Well, okay. If T is not the same as mg and there is a leftover force, that leftover force must clearly be responsible for acting on this section of the string. And if I consider this section, then I would say delta F must be equal to, let's call this some ms. So this section of string has mass ms. Okay. But if ms is 0, we've considered massless strings. If this ms is 0 and this delta F is non-zero, what should be the value of A then? If I try to calculate the acceleration of the string, this would be what? Can you divide something with 0? No, this would not even be defined. And if you consider this to be some really, really small mass, not being 0 exactly, but something really small, this acceleration would be a very large quantity. This would tend to 0 or infinity, right? So if this somehow approaches 0, then the acceleration tends to blow up. And we know that can't be true. So the only way to reconcile this, so the only option for us to have So the only option is for us to accept that the tension is the same everywhere in the string, if the string is massless. If the string has some mass, a more realistic example would be, let's say instead of a string you consider a chain, consider an iron chain or a steel chain or something like that, then yes, then you really cannot make the assumption that the string is massless and get away with it. Your dynamics and all your calculations would come out absolutely wrong. And then you really would have to sit down and figure out how much the force decreases as you move along the length of a chain, decreases or changes, whatever the case might be. But given our assumption that the string is massless, we can safely assume that TL and TR are the same. So in our example, since the string is massless, TL must be the same as TR. So tension on both sides of the on both sides of the pulley is the same. In fact, it's the same at every point on the entire string. Well, let's just call it T. So the free body diagrams will now look like this. Now imagine M1 and M2 are not the same. Right, one is a larger block, one is a smaller block. And if I tell you that M2 is larger than M1, which of these sides, which of these blocks rises up and which of these blocks goes down? The heavier one goes up or goes down? Should go down, right? So if I tell you that M2 is heavier than M1, I can kind of safely assume that M2 goes downwards, yes? So this is, assume and I actually don't really, this is not really a special case because either of the two blocks could be M1 or M2. So it's not like I'm adding anything artificial to the system. So it is still as general as it was before. So let me write down the equations of motion. So assume again all the vectors pointing upwards are positive, all the vectors pointing downwards are negative. So what would be the equation of motion for M1? For M1, I would have T minus M1G must be equal to M1 times A. M1 rises up. What about M2? What are the forces on M2? What are the forces on M2? Speak up, speak up. If you're this silent, there is no way you can be engaged enough to actually understand what's going on. Speak up. What are the forces on M2? Just look at the free body diagram. Once you've drawn this, you should be able to pick up the forces and the accelerations. But, well, that is true. Although the convention I've used is that upwards is positive. Your convention assumes that downwards is the positive direction. Right? No, you're right. Yeah, no, you're right. You're right. You're right. So T minus M2G is minus M2A because acceleration of M2 is downwards. All right, so I have the two equations. T minus m1g is m1a. T minus m2g is minus m2a. If I wanted to solve for acceleration, I could subtract the second equation from the first one, right? So this becomes a minus t, this becomes a plus m2g, this becomes a plus m2a. And that gives me m2g minus m1g must be equal to m1a plus m2a. So I'm going to factor out a here from these two terms because that's what I want. So I can write a times m1 plus m2, and just to make it look very nice, I can factor out the g from these two terms too. So a m1 plus m2 must be equal to g m1 minus m2. And to calculate a, I just divide both sides with the term m1 plus m2. So I get, all in all, m1 minus m2g over m1 plus m2. Okay, so now we can think about that one special case where we said what happens if m1 is the same as m2. What happens if m1 and m2 are the same? What happens to the acceleration? There is no acceleration, this is 0, right? If m1 and m2 are the same, the numerator becomes 0. Regardless of what m1 and m2 are, if they are the same, I don't have any acceleration. Does that mean the blocks on the pulley can't move? If the acceleration is 0, can the blocks still move? Or they cannot move? Can they move? Anyone who says yes or no, either way, some answer. Okay, think about it. I won't tell you the answer. Because the thing that you can see is this is going to be smaller than the acceleration due to free fall. There's a mistake here. Oh yeah, there's a negative sign. Sorry. Thanks for pointing that out. That should have been m2 minus m1. Okay, but this acceleration is it the same as free fall? Is it like if I just take a block and I let it go? Is it that at least? No, right? It's obviously going to be less than that because there is some other term that's being subtracted and it's being divided with the sum of the masses of both the blocks. So all in all, the acceleration is going to be less than the acceleration due to gravity. Now this might look like a very silly, simple toy system, but it actually has a lot of uses. And one of the uses is part of your homework that was uploaded yesterday. You can build machines that multiply force by hooking up pulleys in very clever ways. So take a look at the homework, and you'll actually see that this sort of a system can be very useful to you. Yeah. because this should have been an m2 minus m1, and I have it written as m1 minus m2. Yeah, I kind of flipped the terms around, so I had to pull a negative sign out. Okay. Let's do an example that's a little bit more involved. Let's say I'm driving on a curved road. Okay, I'm just taking a turn. This is I'm horrible at driving. So I'm drawing, so I'm reasonably okay at driving. I'm horrible at drawing, so I'm going to draw a block. That's what any physicist will do. When challenged with drawing, physicists draw blocks, and then we say that it represents reality. That's how it works. But let's say I'm taking a turn, and I'm sort of, so I'm taking a turn like this, and I'm sort of viewing it from this angle. Okay. So this is where the road is. It should be on the road. Right, so I'm essentially taking this sort of. So if I'm going around on a road like this, I'm looking at it from a higher angle. That's how I've tried to draw at least. Okay, how would the normal force act? If I'm driving on this road, let's assume this surface is the road, and I'm driving a car on this surface. What are the forces acting on me? How does gravity act on me and the car? So if I'm driving on this surface, it's going to be vertically downwards, yes, towards the ground. Normal force from the road, yes, because I'm not sinking into the ground. There is a normal force that keeps me on the road. How would that act? Gravity pulls me down, normal force acts upwards. If I'm taking a turn, even if I'm doing it at constant speed, if I'm taking a turn, what is changing? Acceleration is not changing. I'm doing this at constant speed. Velocity is changing if I'm taking a turn. Yes? So if velocity changes, there must be an acceleration. I'm doing this at constant speed, and I'm taking a turn. What kind of acceleration is this? Centripetal acceleration. Very nice. So, well, it's hard to kind of draw the vertical forces on this, but imagine I'm looking at the car. So let's say I'm looking at the car from behind. Okay, at this point, now the car is right. You're right behind me. You're looking at me taking the turn. Gravity, if it points downwards to counteract it and keep me on the road, the normal force points upwards from the road. How should centripetal acceleration be if I want to take this turn? How should centripetal acceleration look? Okay, well, look at this situation. How would centripetal acceleration look? Where would it point? Yes? So if I'm looking at it from behind and I'm going this way, right? I'm taking a turn this way. How would centripetal acceleration look? To the right again. Do I have any force acting to the right here? How am I even getting the centripetal force, acceleration? There must be some force. Friction. Exactly. What happens if I don't have friction? When driving on ice, I try to take a turn, what's going to happen to me? I'm just going to keep going straight. My wheels are going to turn in place, nothing is going to happen. I'm going to go off the road and crash. Agreed? Yes? This is also the perfect weather for an experiment. By the way, don't go sliding off the road. Take an object and slide it. It will just, even if you slide it on a curve, it will just go off the curve. There is no way anything can turn it. So friction is going to make me turn. So let me write down the equations of motion for this. Along y, if I call vertically upwards to be plus y, and if I call to the right to be x, along y, Fs must be mg. And along x, what are the forces I have? Friction. It's really the only force. What is the acceleration? It's AC. So friction must be equal to MAC. See, there is no special thing as a centripetal force. It is just the way a force acts on an object that causes it to behave as a centripetal force. And if I'm holding up a block with a string, it's just tension in the string. If I were to take that block and if I were to spin it, that tension would provide the necessary centripetal acceleration to the block, and hence it is referred to as a centripetal force. Any force can take on the role of a centripetal force depending on the situation, right? So you have to identify what is the force that's causing my block or my car to make this turn. In this case, it turns out to be friction. If there is no friction, I try to make a turn, I can't make this turn, I just go flying off the road. Because there is friction, it pushes me in. All right. So how does friction behave? You know that there are two kinds of friction. One is static friction, one is kinetic friction. Yes? Okay. Which one of these is it? Is it static friction or is it kinetic friction? Static, he says. But the car is moving. Why shouldn't it be kinetic friction? Sure, but it's still moving. I don't know. That's what I'm asking you. Why not? You have to speak up. Well, in what sense? Sure, but even if there were, is this friction static or kinetic? Okay. When does kinetic friction kick in? When you have a surface, you have an object on top of that surface, and you're sliding. Yes? There is relative motion between these two surfaces, yes? If your tire were sliding on that road, are you in a very nice driving position? Your car should not slide on the road. At the point that it makes contact with the road, it sticks. It's not sliding against the road. Do you agree with me? Ideally, at least. So this must be static friction. Is that okay? All right. How does static friction behave? What is the characteristic of static friction? How does it behave? If I were to take this, if I were to take this eraser and I pushed a little bit, what happens to how does friction react to the way I push and pull on it? What are the features of static friction? Is it always a constant? Is static friction always constant? Is it always the same? You're saying it's always this? Well, okay. So let's say I have a coefficient of static friction μs. So times, Fs. Okay. Assume this is half a kilo is reasonable assumption. So this is half a kilogram, okay? 0.5. Now imagine that there is some coefficient of friction between this stack of sheets and this surface. So let's say that's 0.5 again. We'll make lives easier for ourselves. And assume acceleration due to gravity, just assume it's around 10. So this works out for that sheet of papers and that surface. How much would it be? 0.5, yes? Okay, draw a free body diagram. If I were to take this stack and I were to push it a little bit, you're saying this force is 0.5 Newton. And if I were to apply just the tiniest bit of force, let's say 0.1 Newton, what is the net force? What is the net force? 0.5 this way, 0.1 this way. 0.5 in one direction and 0.1 in the other direction. 0.4. So if there is a net force of 0.4 this way, my stack of sheets is going to start moving this way. Yes? If I am pushing on this with a force of 0.1 Newton, do I see the stack come flying back at my face? Do you see the point I'm trying to make? Static friction cannot be a constant. It will only do as much as is required for me to keep, for the stack of papers to remain in place. This is it's a subtle but important point. Just because I apply a little bit of force on it, if static friction were to just act at its maximum, everything would come flying back at me if I tried to push it. That would be fantastic. All I needed to do to make things move would be to tap it a little bit and get out of the way. Friction would just move things around. I would have solved the world's energy crisis. I'd get at least one Nobel Prize for that. So my point is this. For static friction, it is never always equal to mu Sn or mu Fs. Don't blindly or from your formula sheet just plug in mu Sf. It doesn't quite work like that. Kinetic friction, on the other hand, is always mu k times Fs. Because once the object starts sliding, friction says, well, I don't care anymore. I'm going to give you this much amount of resistance, and the rest is up to you. But static friction, if it were to be this constant force all the time, objects would start moving with the slightest touch. That is clearly not the case. And the reason I'm saying this is because I don't know how much the frictional force is yet. It's just that if I am driving at a reasonable speed, it is just enough to make sure I take that turn. However, it's limited, right? It cannot it cannot be larger than a certain value. So beyond a point, if I take the turn too fast, what happens? If I take a turn too fast, I demand a much larger centripetal acceleration because AC goes as v squared over r, yes? So the value of AC I need to make that turn shoots up. And the friction has to work harder to make sure I get that much amount of acceleration to take the turn safely. But beyond a point, it can't do much. It can only be this much at most. So there is a limit on how fast I can take a turn. So if I want to calculate the maximum speed that I can take this turn with, So now I can say, and Fs is mg from my x equation. This equation I can rewrite along y along x as mu s mg is mv squared over r, where r is some, is the radius of this turn, of the arc that I'm traveling. I can get rid of the m's, divide both sides with an m. And this is V max. So the maximum speed I can take a turn with, assuming there's friction, is mu s times r times g. Any faster than this, and friction will not be able to keep up with the requirement that I take the turn safely. It's going to keep giving me that much, or well, I'll start sliding. It's going to give me mu k times Fs, but that is not nearly enough for me to take the turn. I am going to slide for sure. Has anyone seen F1 races or NASCAR races? Just even a small snippet of it. Do you see how the roads are? So one way people compensate for lack of friction is by changing the angle of the road itself. It's called banking. Even all your highways are also banked to a certain angle. Not quite as dramatic as racetracks, but they are banked. So if this car were to be on a banked road, this free body diagram, instead of being on level ground, would actually be on an incline. I'm just going to, well, okay, let's take a turn this way. The acceleration is still towards the right because I'm still taking a turn the same way. It's like the road, it's just the road that is tilted. Gravity still pulls me downwards. I assume I have no friction, and you'll see that it is possible to take a turn on this sort of a road. Even if there is no friction, if you have just the right speed, you can take a turn. How would the normal force look? Vertically up? How does the normal force, what is the meaning of the word normal? Normal means perpendicular to the surface. So normal force looks like this. Okay, and I'm just going to write down the equations of motion and we'll go to the quiz. If I consider to be the horizontal direction to the right as plus x, if I consider vertically upward direction to be plus y, then part of the normal force, this component, balances gravity, and there's a component of normal force along the x direction. That component provides me the centripetal force that I need to make the turn. I don't think we have time to do the whole example today. Rance will probably pick it up on Thursday. But the idea here is that banking gives you a component of the normal force in the horizontal direction, and that is good enough in a lot of cases to keep you from going off the road. Okay.